Good afternoon, students. Welcome in next lecture of Math F212 optimization. So presently we are doing simplex method. Audio video is okay.
Yes, sir.
So let us first brush up the simplex method. So for the simplex method, I have taken the question of ready-mix problem. So you have the idea what is the ready-mix problem. Then we have done the following formulation. So in the formulation, we have the four constants, two variable, and it is of maximization problem. Then we have solved this problem by the graphical method, and here we have seen at the point C. At the point C, we have the optimal solution x1 is equal to 3, x2 is equal to 3 by 2, and z is equal to 21. So from the graphical solution, we have optimal solution at the C that we have seen. Now we have converted this into the standard form using the slack or surplus variable. Since all the constraints are of less than type, so we require only the slack variable to make it as a standard form. So using the s1 s2 s3 s4, we have made the given problem into the standard form or equation form. Here you can notice we have the m is equal to 4, means 4 equations or 4 constraints. N is equal to 6, means total number of the variables are 6, x1 x2 s1 s2 s3 s4. So by the theory we have, if you want to find the solution, unique solution or corner point or intersection point of the two lines, then we have to consider number of the basic variables are whatever the number of equation, that is equal to 4, and remaining variables are n minus m, are the non basic variable. So if you use the algebraic method, total NCM or 6C4 or 15 system of equation we have to solve. So when we solve the 15 system of equation by considering any two a non-basic variable, remaining 4 as a basic variable, we have the solution. So some solution may be a feasible solution, some are non-feasible solution. And for the feasible solution, we compute the value of the z, and wherever we have the maximum value of the z, there we say it is the optimum value. Then after, uh, so this is the standard form. And for the objective function also we will do that all the variables are on one side and all the constant on one side. So from this we have the this initial table, right? Here we have the initial table. So this is the initial table. So from the first problem, we means from the problem we make the initial table. So here we can note, here we write the basic variable, here we write the all variables. So z, x1 x2 s1 s2 s3 s4. So z is also one variable. Later on, because its entry will be always the 1000, so always means later on we will omit to write, but it is also one variable. So after checking the optimality condition, we decide which non basic variable come in the pool of the basic variable. And after checking the feasibility condition, we decide which basic variable will go in the pool of the non basic variable. Means entering variable we decide with the optimality condition, and leaving variable we decide with the help of the feasibility condition. So if the problem is of maximization, then we decide the entering variable by checking the most non-negative variable or most non-negative coefficients in z row. If it is the problem of minimization, then we check for the most positive, right, coefficient. So after deciding the pivot column, we check the feasibility condition by taking the minimum ratio of right hand side or solution, and the element of the entering column, and wherever we get the minimum ratio, that will that variable will be the leaving variable. So means after checking the feasibility condition, then we do the Gauss Jordan row operation only row operation you have to do. So then we perform the Gauss Jordan row operation, and we make that entering variable as a basic variable. So what is that? In that case, we make right entering variable. So whatever we have the so here we have the minimum ratio. So here we have the minimum ratio. So this is your pivot element. This is your pivot element. So we make it is 1, and all the other entries in that column as a 0. So here we will get the here we will get the right. So this is the pivot element. So after the proper Gauss Jordan operation, you can see here you will get the 1 and rest as a 0. Rest as a 0 means always all the basic variable will form the identity matrix 1, right? Then after 1, 1 and 1. So here we have the x1, s2, s3, s4. So they will form the right identity matrix. So in this way we proceed. So we proceed until unless we will get the optimal table. So this thing last time we have done. So here we have the summary. So what we have to do in the first step? In the step 1, determine the starting basic feasible solution. First you have to start from where we have to start the table. Then select the entering variable using the optimality condition. What is the optimality condition? If problem is of maximization, then we check most negative. Most negative. When the problem is of minimization, then we check the most positive. Most positive. Right? After deciding the entering variable, we have to decide the leaving variable. So we decide the leaving variable using the feasibility condition. Feasibility condition means minimum ratio. Minimum ratio. Minimum ratio of right hand side and element of the entering column. Then we determine the new basic solution using the Gauss Jordan row operation. Only the Gauss Jordan row operation. So after having the optimal solution, we may perform the two analysis, either the post optimal analysis or sensitivity analysis. So that is the last part. So in last I will cover this part. So what is the sensitivity analysis, which deals with determination of the condition that will keep the current solution as a unchanged. Means what is the range of alteration? What is the range of alteration in which we can alter our variables, so that the current solution will be the unchanged, right? Current solution remain unchanged. And post optimal analysis, by doing if there is some disturbance, how we can regain that, how we can regain the optimal solution from the current optimal solution. So that is the post optimal analysis. So that is the last part. In the last we will do. So in continuous of the simplex method, now we will see some good question related to simplex method. So please see carefully to make it clear, means all the concepts. So here very first question, this problem is designed to reinforce, means that is not a means correct step. Just to clear the concept, we are reinforcing, designed to reinforce your understanding of the simplex feasibility condition. In the first table, of example 3.1, we used minimum non-negative ratio test. That is the actual procedure, right? Minimum non-negative ratio test to determine the leaving variable. Such condition guarantees that none of the new new values of the basics variable will become negative. Means by taking the minimum ratio test, we guarantee that always we get non-negative, right? Means we guarantee that none of the new values of the basic variable will become the negative. right? Now, to understand this, to determine this point, force S2, force S2 instead of the S1 to leave the basic solution. Now, look at the resulting simplex table, and you will note that S1 assume a negative value. Assume a negative value, meaning that new solution is infeasible. This situation will never occur if you employ the minimum ratio feasibility test or feasibility condition. See, that is our first table. Now see the first table. That is our first table. That is, you can say from the graph, it is the point A. In the graph, it is point A, right? So very first table we have. So what is the entering variable? Now please see carefully. What is the entering variable? Where we have the most negative, because it is the same ready-made problem. So most negative will enter. So most negative will enter in the system. Now this is the uh, pivot column. This is your pivot column. Now this is your right hand side, right? This is your right hand side. So we take the ratio. We take the ratio of right hand side and the element of the entering column. So here we have the 24 by 6. Here we have the 6 by 1, and these ratios are not possible because here the coefficients are negative, and here the elements are negative or 0. So that ratio is not possible. So what is the actual theory? We take the minimum ratio. So in actual we have taken this as a living variable. Now to understand the concept, what they are saying, that you assume, instead of the minimum ratio, you assume that this is the living variable. This is the living variable. It means forcefully this is your pivot element. Forcefully this is your pivot element, means S2 is the living variable. S2 is living variable, and X1 is the entering variable. X1 is entering variable. X1 is the entering variable. So in place of the S2, now X1 will enter. So when in place of the X2, X1 will enter. So now we make it, right? We make it is 1. So it is already 1. So need not to do any Gauss Jordan row operation. Then we have to make this 6 as a 0, this minus 1 as a 0, this 0 as a 0, and this minus 5 as a 0, using the appropriate Gauss Jordan row operation. So here we have the 0, here we have the 0, here we have the 0, here we have the 0. So after performing this, you can note that here you will get the value of S1. S1 is equal to minus 12. Here you will get the value of the S1 as a, so here you will get the value of S1 as a minus 12. But in question always we take all the values, all the variables, x1, x2, s1, s2, s3, s4, all must be non-negative. But here it is coming the minus 12, negative. It means this table is nothing. This table is the infeasible table. This table is infeasible table. So automatically from the graph you can note this thing. In last class I have told you this. So if the x1 is entering, if the x1, let us have the clear graph. If the x1 is entering, x1 is entering variable. So what is the intercept? What is the intercept with s1 is equal to 0 and with s2 is equal to 0 line? Here we have added the s1, here we have added the s2. So this line corresponding to s2 is equal to 0, this line corresponding to s1 is equal to 0. So when x1 is entering, then what is the intercept with respect to s1 is equal to 0 and s2 is equal to 0 line? That we are computing in the ratio. So it is nothing. It is the 24 by 6, and this is the 6 by 1. So that's why here we have the 6, here we have the 4, and from the graph you can note down this is the infeasible point. This is infeasible point. So the same thing you are getting from the table. That's why always we prefer the minimum ratio. Minimum ratio feasibility condition. Minimum ratio feasibility condition, because it guarantee the feasible solution in the next table, in the following table. It guarantee the next, it guarantees the feasibility of new solution. Clear? I believe there is no problem in the Gauss Jordan row operation. Clear this question?
Yes, sir. It's
From the
clear.
graph, what I want to convey, it's clear. From the graph, from the table.
Yes, sir. It's clear.
Yes. Now let us have the another question. Consider the following set of the constraints. So here we have the set of the constraints. Solve the problem for which for each of the following objective function. So we are solving only this problem, right? D part. So here we have the minimization of the z is equal to 5x1 minus 4x2 plus 6x3 minus 8x4, subject to subject to constraint x1 plus 2 x2 plus 2 x3 plus 4 x4 less than equal to 40, similarly less than equal to 80 and less than equal to 10. So all are less than, it means you have to add the slack variable. Let's say s1, let's say s2, let's say s3. So here the s1, s2, s3 are also non-negative. So the very first table we have to make. So here we have to make the x1, x2, x3, x4, s1, s2, s3. On the right hand side we have to make solution. Here we have the z, and always I have told you initial basic feasible solution always given by the base slack variable. Please note down these words. Initial basic feasible solution always given by the slack variable, means here the basic variables are s1, s2, s3. Initial basic feasible solution always given by the slack variables. And on the right hand side we have the 40, on the this here we have the 8, and here we have the 10, and here we will get the, now this minimization you will take on this side, so it will become the z minus 5x1 plus 4x2 minus 6x3 plus 8x4 is equal to 0. So here we will get the 0, and here we have the minus 5 plus 4 minus 5 plus 4 minus 6 minus 8 and 0 0 0, and here it make the 1 1 1, right? 1 0 0 0 1 0 and 0 0 1. And here the entries will come for the corresponding to x1, it is the 1 2 4, 1 2 4. Then we have the 2 minus 1 minus 2, 2 minus 1 minus 2, 2 2 minus 1 minus 2. Then we have the 2 1 1, 2 1 1, it is the 2 1 1, right? Then we have the 4 2 minus 1. Yes, 4 2 minus 1. So here we have the 4 2 minus 1. So this is your initial table. So I believe there is no problem in in writing the initial table, in recognizing what will be the initial feasible solution. Always the solution must be in all the table, solution must be the feasible. In the simplex method, always solution in the first table, in the last table, in the intermediate table, always the solution must be feasible. So this is your first table. This is your first table. So here the problem is of minimization. So minimization, in the minimization, non-basic variables are, instead of the S1, S2, S3, here it is written the S5, S6, S7. There is no problem. Now, non-basic variables are for the first table. For the first table, non-basic variables are X1, X2, X3, X4. Problem is of minimization. Problem is of minimization. Then we check the most positive. So this is the candidate of improvement. This is the candidate of improvement, right? So these two are candidate of improvement because the here the coefficients are, right, plus 4. Here the coefficients are plus 8. So these two are, these two may be, means may enter in the system for the next table. Then we have to check the most negative. So most negative is the, right, most negative is the plus 8. So here we have made, right, so here you have to make the arrow besides the x4. So x4 will enter. Now we take the ratio. So when we take the ratio, when we take the ratio, so ratio will be what? It is the 40 upon 4, 40 upon 4, then 8 upon 2, 8 upon 2, and 10 upon minus 1. So 10 upon minus 1 not possible because this is the minus negative. So 40 upon 4, that is your 40 upon 4, that is the 10, and 8 upon 2, that is the 4. So minimum ratio is 4. So it means this is your living variable. This is your living variable, and this is the pivot element. This is your pivot element, means this is the pivot column, and this is your pivot row. Pivot row. So 2 is the, right, 2 is the pivot element. So with this 2 we make the 1. With this 2 we make the 1 by doing the operation what, right, means s6. S6 is the living variable and x4 is the entering variable. So in place of the s6, now the x4 will come here. Now the x4 will come here. Now we have to make this 2 as a 1. So for making the 2 1, we have to divide the whole equation by 2. So divide by 2, 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 and divide by 2. So here 2 upon 2, 1, minus 1 upon 2, minus 0.5, then 1 upon 2, zero point 0.5, 2 upon 2, 1, 0 upon 2, 0, 1 upon 2, zero point 0.5, 0 upon 2, 0, and 8 upon 2, 4. Then we have to make this as a 0. So for making this 0, what the row operation you have to do? Right, we have to make, anyone please tell me what the row operation we have to do for making this 0? Yes, anyone? Yes. S5 minus S4 divided by 2 into 4. If you do this operation, so this will become 0, right? So over the all rows, means over the all elements of the this row, you have to perform the same operation. So here you will get the 1 minus 2 upon 4, right, or 2 upon 2, 2 upon 2, right, 2 upon 2 minus 4. So 1 minus 4, that is the minus 3, minus 3. 2, right, 2 minus 2 minus of minus zero point 0.5, so it will become the, right, so it will be the 4. Similarly we have all the entries. Then we have to make this as a 0, minus 1 as a 0. So how we can make the minus 1 as a 0? For that, what we have to do? S7, row S7 minus, row S7 minus S6, S6 by 2, right? And row 7 plus, plus. So 1 minus 1, it will give the 0. So it is the 0, right? This is your 0. So what we have to do? S7 plus S6 by 2, right? So 6, 4 and S6 by 2, that is the 1. So 4 plus 1, that is your 5. Minus 2 plus 1 upon 2, right? 1 upon 2. So that will give you minus 2.5 and so on. So all the entries will come here. Now we have to make this as a 0. We have to make this as a 0. So when we make this as a 0, what will happen? What the operation we have to do? We have to do the Z row minus S6 upon 2 into 8 into 8. So that will become 0 and you will get the new table. So when we have the new table,
Sir, is there a possibility that after performing multiple, like generating multiple tables, also we are not able to derive an answer and we are continuously getting positive and negative Z values?
means that is possible. There is a cycling and non-terminating cycling we can get. That is one special case. We call that as a degeneracy.
Sir, so how we should identify that? Because we will
Before that,
just.
we have to say that it has a degenerate solution. That is the
Or,
special case, and you have to say we have the degenerate solution. That I will cover, right? That I will cover.
all right.
So now we have the this table. Problem is of minimization. So positive, most positive Z coefficient variable will enter. It means here the this is the negative, this is negative, this is negative. These are the non-basic variable and their Z coefficients are negative. So only the candidate for entering will be the x2 because its coefficient is the positive. So when it is entering, so we take the ratio of right hand side and element of that column. So this ratio is not possible, this ratio is not possible. Only the possible ratio is 24 upon 4. So only one, that is the minimum ratio. It means this is your pivot element. So pivot element we have to make the 1 and rest element as a 0 by the Gauss Jordan row operation. Gauss Jordan row operation. Now in this table you can see the x2, x4, s7 are the basic variable. It means x1 non-basic variable, x1 is the non-basic variable, x3 is the non-basic variable, and s5 is the non-basic variable, and x2, x4, s7, and s6 is also non-basic variable. Now important thing is coming here. The z coefficient of the basic variable x2, x4 and x7 always 0, always 0. But for the basic variable it may be 0, right? It may be 0. For the basic variable, it may be 0, but for the basic variable, always 0. And the z coefficient, here we have the -7, here we have the -10, here we have the -2, and here we have the 0. It means nowhere we have the positive. It means this is your optimal table. Here you have to stop, and this is your optimal table. It means answer is the x2 is equal to 6, x4 is equal to 7, and s7 is equal to 29. S7 is equal to 29. That is the answer. And z is equal to -80. Z is equal to -80. That is your solution. Clear? Means here we have the x1 is equal to 6. No, x2 is equal to 6. X4 is equal to 7. And z is equal to -80. So here in this, if you put x2 is equal to 6, x4 is equal to 7, x1 is equal to 0, x3 is equal to 0, x3 is equal to 0. So what you will get? -4 into 6, 24, and here you will get -8 into 7, that is the 56. So that is coming the z is equal to -80. -80. Clear? So you have seen we have solved the maximization problem as well as minimization problem. Just you have to change the optimality condition. Feasibility condition for both problems are same. Now, now please see the question carefully, because now we are doing the special question. Consider the following system of equation. This is the system of equation. Let x5, x6, x7, x8 be the given initial basic feasible solution. That is the always the first identity matrix variable will be the initial basic feasible solution. So x5, x6, x7, x8 be the given initial basic feasible solution. Solution. Suppose that x1 become entering. It means non-basic variable are non-basic variable are for the first table. Non-basic variable are x1, x2, and x3 are the non-basic variable. So any one can be the entering variable. Any one can be the entering variable. So now question is, if x1 become basic, if x1 is the entering variable, which of the given basic variable must be non-basic at zero level to guarantee that all the variables remain non-negative, and what is the value of the x1 in the new solution? So if I am saying that x1 is entering, x1 is entering, so we have to take the ratio of, anyone please tell me if what is the ratio? If x1 is the entering variable, then ratio will be right hand side upon element of the entering column, 4 upon 1, 8 upon 5, 3 upon 2, and this ratio is not possible. So here it is the 4, here it is 1 point something, and here we have the 1.5. So how much it will come? 0.3, so 1.6, right? So minimum is, this is the minimum. It means x7 will be the leaving variable, x1 is the entering variable. X1 is the entering variable, x7 is the leaving variable. At that time, what is the value of the 3? Right, what is the value of the entering x1? What is the value of the x1? That is the 3 by 2. Whatever this ratio, that is the things. So here we have the, if x1 is the entering variable, then ratio is the 4 upon 1, 8 upon 5, 3 upon 2. This ratio is not possible. So x7 is the minimum value. So x7 is the leaving variable. At that time, the value of the x1 will become the 1.5. Whatever this ratio, the same value will come for the x1. Same thing you have to repeat. Repeat the procedure for the x2, x3, x4. So if the x2 enter, then the ratio will be the 4 upon 2 dash 3 upon 3. So 3 upon 3 will be the minimum. So x7 will be the living variable. At that time, 3 upon 3 is equal to 1. That will be the value of the x2. If x3 is entering variable, then x8 will be the living variable. If x4 is the entering variable, in that case, x5 is the living variable. X5 is the living. So depending what is entering, we may have the different living variable. Clear this question? Just I have chosen this question to clear the basic concepts of the simplex table. Iterations, deciding the which one is the entering variable, which one is the living variable. For such small thing, I have chosen these questions. Consider the following LP. Maximize z is equal to x1 subject to 5x1 plus x2 is equal to 4, 6x1 plus x3 is equal to 8, 3x1 plus x4 is equal to 3. Solve the problem by inspection. By inspection. Don't use the Gauss Jordan rule operation. Just you have to do by inspection. And justify the answer in terms of the basic solution of the simplex method. So, if you have to draw the simplex method, in that case, it will be the z minus x1 is equal to 0. So, what is the z coefficient? What is the z coefficient for the x1? Z coefficient for the x1. If you make the table, if you have not to make the table, by chance, if you have to make the table, what will be the structure of the table? Z, x1, x2, x3, x4. 1. It is the minus 1, 0, 0, 0. And since they are forming the identity matrix, so they will be the initial basic variable, initial basic feasible variable. So x2, x3, x4, in that order you write. And here we have the 0, 0, 0. And here we have 5, 6, 3, 5, 6, 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. This is your initial table. Now, question is of maximization. So x1 is the non-basic variable. Its coefficient, z coefficient value is the minus 1, means negative, has a power to improvement, right? Power for the improvement. So x1 will be the entering variable. If x1 is the entering variable, so we take the ratio, 4 upon 5, 8 upon 6, 3 upon 3. So that is your minimum. So that is your minimum. It means x1 will replace the x4 in the next table. X1 will replace the, here in the next table we have the x2, x3, and x1 and x1. And here we have the minimum ratio. And I have told you on the right hand side, presently we have the 483, 483. So on the right hand side, it will come the whatever the minimum ratio 3 upon 3, that is the 1 that will come. So now here we are performing the simplex iteration. But if we have not to perform the simplex iteration, then from the question itself, it is clear that x1 is a non-basic variable and has the capacity to improve the solution, because z coefficient is the negative. So if you take the x1 ratio, minimum ratio, so here we have the uh, not 4 upon 5 is the minimum. I have taken, I think, 3 upon 3. So this means this is the x4 will remain, and here the in place of the x2, x1 will come. and here we have the 1. We have taken the ratio 4 upon 5. So this is your minimum. This is your minimum, not this minimum. This is the 1. That is the 0.8. So in this case, here you will get the 0.8 instead of the 1. Here you will get the 0.8. So in the next table, x1 is the 0.8, x3 and x6, x4 we have to compute. So here x2 basic variable x2, its ratio will be the 4 upon 5, that is the minimum. X2 will leave, x1 will enter, and after entering, its value will be the 4 upon 5. So x1 value is the 4 upon 5. What is the value of the x3? What is the value of the x3? So x3 is the what we have to do? We have to make it as a 1. We have to make it as a 1 and this as a 0. So for making this as a 0, what we have to do? We have to do the 6 upon 6, that is the 1 into 5. So 5 minus 6 upon 6 into 6, right? Into 5. 5 minus 6 upon 6 into 5. That we have to do. It means what the operation we have to perform? Here we have to perform the operation x3 minus x3 no x2 minus x2 minus x3 upon 6 into 5 into 5. So from there you will get the value from for this position, value for this position. And what is that value? That value will be the 8 minus 6 into 0.8, that is the 3.6. Similarly, corresponding to x4, we have the 3 minus 3 into 0.8, that is the 0.6. So after doing this operation, here you will get the 3.6 and here you will get the 0.6. So that means for writing this, there is no requirement for making the simplex table. Just just remember that only it is the there is one non-basic variable which is entering, right? So you can compute the ratio and corresponding change in the value of the basic variable will come automatically, right? So when we put the value of x1 in the z, or you will get the answer of the z as a 0.8. Now in the b part, repeat assuming the objective function is of minimization. Here we have, now please see carefully, z is equal to x1, minimize z is equal to x1. So you will write the z minus x1 is equal to 0 in the very first table. In the very first table, right? Z, x1, x2, x3, x4, here we have the 1, here we have the minus 1. So which, and here we have the 0 0 0. So which non basic variable come in the problem or will become the basic variable? Which non basic variable has a capacity of improvement when the problem is of minimization? No variable has that capacity. It means the current table is the optimal table. So whatever the current answer, x2 is equal to whatever the current answer, right? Whatever the current answer, x2 is equal to 4, uh, x3 is equal to 8, and x4 is equal to 3. That will be the optimal solution. And z is equal to 0 is the minimum value. Current table is optimal table, current solution is optimal solution, and current solution is what? X2 is equal to 4, x3 is equal to 8, x4 is equal to 3, and z is equal to 0. Now, next question. If you feel any doubt, please stop me at that place and ask. Solve the following problem by inspection. Justify the method of solution in terms of the basic solution of the simplex method. z is equal to 5x1 minus 6x2 plus 3x3 minus 5x4 plus 12x5 subject to this constraint. So here, when we write in the equation form, here we have to add the slack variable. So here we have added the slack variable. That slack variable is also non-negative. So x1, x2, x3, x4, x5 and s1 are non-negative. Constraint will become x1 plus 3x2 plus 5x3 plus 6x4 plus 3x5 plus s1 is equal to 90. So, and when we make the simplex table, so here we have the z minus 5x1 plus 6x2 plus minus 3x3 plus 5x4 minus 12x5. So in the very first table, can you tell without making the table? Can you tell which one is the basic variable? Which one are the non-basic variable? For the initial table, which variable is the basic variable?
S1,
S1 is the basic variable, and non-basic
X1,
variables.
X2, X3, X4, X5.
Correct, right? And problem is of maximization. So which has the maximum has the capacity of the maximum improvement?
X5.
X5, since the coefficient is the minus
Minus.
12. So when the x5 will enter in place of the s1, because we have the one constant only. So the what is the value of uh, x5? We take the ratio, and whatever the ratio, that is the value of
Minus
the x.
1.5.
No, ratio is the 90 upon 3.
Oh, okay. 30.
90 upon 3, na?
Yes, sir.
Right hand side and element of the entering column. So that is the 30. So in next table, the z will come the 30. So here, the basic solution. Now please see, I am summarizing the things. So basic solution consists of one variable each. Thus, means here we have the only one constant. Here only we have only the one constraint, right? So one constant means at a time we have only the one basic variable. At a time only we have only one basic variable. Basic variable may be x1, maybe x2, maybe x3, maybe x4, maybe x5. So if you assume, let x1 is the basic variable. So if the x1 is a basic variable, then the ratio will be the 90 upon 1. 90 upon 1. If x2 is the basic variable, 90 upon 3. If x3 is the basic variable, 90 upon 5. If x4 is the basic variable, 90 upon 6. If x5 is the basic variable, 90 upon 3. So here you will get the, if x1 is the basic variable, then x1 will be the 90 upon 1, right? 90 upon 3, 90 upon 5, 90 upon 6, 90 upon 3. At that time, what is the value of the z? Means if x1 is the basic variable, then x1 5x1 will be the solution. Rest are 0 because they are the non-basic variable. If so, 5 into 90, that is the 450. At that time, the value of the z will be the 450. When x2 is the basic variable, then x1, x3, x4, x5 are at 0 level, are the 0, and x2 is equal to what? X2 is equal to 30. So the z is equal to, it will become minus 6 into 30, that is the minus 180. So here the value of the z is coming the minus 180. When x3 is the basic variable, at that time x1, x2, x4, x5 are at the 0 level, and the z will be the 3 into 18, that is the 54. So we check for all, and for among all, the z is equal to 450 is the maximum. So that is your optimal solution. At that time you take the x1 is equal to 90, and x2, x3, x4, x5 are the non-basic variable at the 0 level. at the zero level. So that's all from my side for today. If we have some more good question, in next class we continue. Clear? What is the simplex method? Still, if you have any doubt, you can discuss. If otherwise, you can leave. Thank you all.
Thank you, sir.